Welcome to Chapter 1 of our signal processing course. Today, we will explore two fundamental mathematical tools, convolution and correlation. These concepts are the bedrock of how we analyze signals and understand how systems transform those signals from input to output. Let's begin with the definition of convolution. Mathematically, the convolution of two signals, xt and yt, is represented by an integral where one signal is flipped and shifted across the other. While it can be difficult to visualize this physically at first, think of it as a way to calculate the overlap between two functions. It is absolutely essential for characterizing the behavior of linear time invariant, or LTI systems, which we will discuss later. Convolution has some very convenient properties that make our lives easier. First, in the frequency domain, convolution becomes simple multiplication. This is a powerful shortcut. Second, convolving any signal with a Dirac impulse, or delta function, returns the signal itself, much like multiplying a number by 1. Finally, convolution is commutative, meaning the order of the signals doesn't matter. X convolved with Y is the same as Y convolved with X. Continuing with properties, convolution is distributive, so you can convolve a signal with a sum of signals just as you would in basic algebra. Another fascinating property involves derivatives. The derivative of a convolution is equal to the convolution of one signal with the derivative of the other. This allows us to move calculus operations around to whichever signal is easier to differentiate. Now, let's shift our focus to correlation. Correlation is used to determine how much two signals resemble each other. The cross-correlation, Rxy, looks similar to convolution, but without the time reversal in the integral. When we compare a signal with itself, we call it the autocorrelation function, Rxx. This helps us find patterns or periodicities hidden within a single signal. For real-valued signals, the formulas simplify slightly because we don't need to worry about complex conjugates. Here you can see the standard forms for cross-correlation and autocorrelation for real signals. In both cases, we are essentially looking at the integral of the product of two signals as one is shifted by an amount tau relative to the other. In cases where signals have infinite energy but finite power, we use a limit-based approach over a time period t to calculate the correlation. The key takeaway here is that the correlation function is a direct measure of similarity. The higher the value, the more alike the signals are at that specific time shift. There is a second way to express the correlation integral. By using a simple change of variables, we can show that Rxy is also equivalent to shifting the first signal backward instead of shifting the second signal forward. Both methods yield the same result, providing flexibility depending on which signal is easier to manipulate. You might have noticed that convolution and correlation look remarkably alike. If we take the first signal, reverse it in time, and then convolve it with the second signal, the math works out perfectly to match the definition of cross-correlation. This reveals a deep mathematical link between these two operations. To conclude this comparison, cross-correlation is simply the convolution of a time-reversed version of your first signal with your second signal. Similarly, autocorrelation is the convolution of a signal with its own time-reversed version. This link allows us to use convolution algorithms to compute correlation efficiently. Let's look at some properties of correlation. First, the cross-correlation of x and y is the time-reversed version of the cross-correlation of y and x. Second, the autocorrelation function is always symmetric or an even function because the resemblance of a signal to itself doesn't change whether you shift it left or right. Finally, let's consider what happens when the shift is 0. When the shift tau is 0, the autocorrelation Rxx, 0, is simply the integral of the signal squared, which is the total energy of the signal. We also know that the correlation is always at its maximum at 0 shift. By dividing the function by this maximum value, we get a normalized coefficient between -1 and 1, which tells us the percentage of similarity. Moving on to section 3, we enter the world of linear time invariant LTI systems. These are crucial because most real-world physical systems, like circuits or acoustic environments, can be modeled as LTI systems. We represent these systems as an operator H that transforms an input signal xt into an output signal yt. What makes a system LTI? The first requirement is linearity. A system is linear if the response to a weighted sum of inputs is equal to the weighted sum of the individual responses. In simple terms, if you double the input, you double the output, and if you add two inputs together, their outputs simply add up without interfering with each other. The second requirement is invariance, or more specifically, time invariance. This means the properties of the system do not change over time. If an input xt produces an output yt today, the same input should produce the exact same output tomorrow, just shifted in time. The system's rules are constant. The beauty of LTI systems is that if a system is both linear and invariant, the output is always the convolution of the input and the system's impulse response, ht. This means that ht completely characterizes the system. If you know how the system reacts to a single sharp impulse, you can predict how it will react to any signal in the world. To prove this, if we feed a Dirac pulse into an LTI system, the output is exactly ht, hence the name impulse response. Therefore, we can describe any LTI system either in the time domain using its impulse response ht, or in the frequency domain using its Fourier transform hf, which we call the transfer function. Finally, the transfer function hf shows us how the system filters energy across different frequencies. Because convolution in time is multiplication in frequency, the output energy spectrum is simply the input spectrum multiplied by the square of the transfer function's magnitude. This relationship is the fundamental tool used to design filters and analyze how signals are modified as they pass through any linear system.